we have the derivative of x1 and the derivative of x2. The derivative of x1, can you please read that again, the first equation? Thank you. And the second equation? So we have a system of two equations, and there is no initial conditions. Yeah. So I'm gonna, since we're reviewing this, let's see. Just give me 1 minute, and I'm gonna add initial conditions so we can do this full pronoun. So suppose also that x1 at 0 is 2, and that x2 at 0 is 1. So these equations involve only the first derivative. Therefore, this is first order system, linear system of ordinary differential equations. First order is only one derivative, the first derivative. If these equations were higher order, the initial conditions, we would also need initial conditions on the lower order derivatives, first derivatives, second derivatives, and so on, right? But in this case, we have a first order linear system of ordinary differential equations. First step is to rewrite these two equations as a product of a 2 by 2 matrix times a vector. That part we had worked out something like that before. And remember, we are interested in, we want to find x of t, which means we'd like to find x1 of t and x2 of t. So we want to find the function, the vector valued function that has x1 and x2, such that this function x satisfies that the derivative of x, I use that arrow notation, derivative of x equals p times x. If I wanted to use that notation we were looking at just 2 minutes ago, I could think of this system being written as p times x vector plus f. In this case, f is trivially, this would be considered the f vector that's added to the matrix vector product. And it would be a vector of zeros. So it's kind of boring, not too interesting, but consistent with that notation, that's what we have. So here we would write something like, well, I'm going to write p in a minute, but we want to find x using a theorem we discussed last time, which says that really all that matters is a linear combination of v1 and v2, where v1 and v2 are the so-called eigenvectors. So we take a linear combination of V1 and V2 such that the coefficients in that linear combination involve lambda 1 as an argument of the exponential function, and then also lambda 2 as an argument of the exponential function. So we use E, the exponential function E, evaluated at lambda 1t, and E evaluated lambda 2t, and then we need a constant here, C sub 2. So what we want to do is to compute the solution, okay, compute the solution of this system, this linear system, as a linear combination of the eigenvectors. That means we need to know the eigenvalues and the eigenvectors. So here, part of what we are implicitly assuming there is that P times V sub k equals lambda k V sub k. So lambda 1 V1, they come as a team. Lambda 2 V2, they are the other team, right? So they come in groups. Lambda is called an eigenvalue, V is called an eigenvector. And the idea is that they satisfy this. So we go back to the original formulation of this problem, and we first rewrite. This is matrix vector form. So the matrix here is going to have first row 1, 2. So we write this in matrix vector form. So this would be the vector is the vector of state variables. It contains x1 and x2. The matrix has first row 1 and 2, and the second row has numbers -2, 1. Right? The second row has numbers -2 and 1, and this is equal to the derivative of x1 and x2. So that means that that matrix P, the matrix for which we want the eigenvalues and eigenvectors, this matrix P, in this case, is a matrix of constants. It's not a matrix of things that are changing with time. So when we think of this system as Px plus F, in this case, that F is trivial. This is one of those cases that we would call a homogeneous system of linear equations. So maybe you can write that here. This would be considered homogeneous system of linear ODEs, because that vector F is identically 0. But this is the 0 vector. So we want eigenvalues, right? So this is the work we had done before. So you could do the eigenvalues and eigenvectors by hand, or you could also, what's the other alternative that we have discussed so far for eigenvalues and eigenvectors? Sage Math, right? Cloud Sage Math. So suppose we do that work, and we have lambda 1 equals 1 minus 2i, and this goes with a vector v1, and that vector v1 is, for example, 1 minus I, and also we have lambda 2 equals 1 plus 2i, and a vector v sub 2, vector v sub 2, that's going to be 1i, for example. So we could easily verify that if we multiply the matrix P times this vector v sub 2, that is equal to a vector which is the same as multiplying this value times v sub 2. So for purposes of verification, right, we could verify. I'm just going to verify part of this. So you could verify the first. I can verify here the second one. So that means we can take the matrix P and multiply the matrix times the vector, one of the vectors. So that matrix P has column 1 minus 2, first column 1 minus 2, and second column 2, 1. Okay, so that's the matrix P, first column 1 minus 2, second column 2, 1. We want to verify that with, say, vector V sub 2, which has entries 1 and I. So you could do this by the definition of matrix vector product in terms of linear combination of the columns, or you could do it in the other way. But so you would end up with something that looks like 1 plus 2i on the first entry, and the second entry you end up with minus 2 plus 1i. So what we're doing here is, here's the matrix P, and here's the vector V sub 2. And what we'd like to see verified is that P times V sub 2 matches the product lambda 2 times V sub 2, which is what we do next, right? So let's verify. Here's that same vector. Now let's multiply that by the value 1 plus 2i. So the first entry is 1 plus 2i. The second entry becomes I plus 2 times I squared. Okay, and so I squared is negative 1. So we can write this one extra step here. First entry stays exactly the same, 1 plus 2i. Second entry, we have I, and I squared is negative 1, so this becomes I minus 2. So now we'd like to compare this scalar vector product to the matrix vector product. So we compare the first entry. Here's the first entry, 1 plus 2i. That's the first entry. So this is a match. And the second entry is minus 2 plus 1i. And here is exactly what we have here, minus 1i minus 2. So the second entry is also matched. So this verifies, therefore, we have verified that P times V sub 2 equals lambda 2 times V sub 2, which is the so-called eigenvalue-eigenvector equation. This is what defines V2 as an eigenvector for the specific case of that scalar called lambda 2. Lambda 2 is an eigenvalue because there exists V2 such that this equation is true, which is what we just verified. So what we want to do, and you should do the same for V1 and lambda 1, but now we'd like to consider a linear combination of V1 and V2 such that the exponents of this, well, so what we would do next is to compute, for example, let's compute e to the lambda 1 t. This would be e lambda 1, we said, is 1 minus 2i times t. This leaves us with e to the t, e to the minus 2i t. I'm going to pull that I up front. So I'm going to write this as e to the I times minus 2t. And here's where that formula, Euler's, we said it was called Euler's. So what is Euler's? Maybe I can write here that as a bubble thought. People like, I don't know if you guys watch cartoons, but cartoons were definitely part of my schedules on Saturdays when I was younger. So maybe Fridays and Wednesdays too. Sometimes Mondays. So e to the I theta cosine theta plus I sine theta, right? And then, not exactly this is how it looked, but the Coyote and the Roadrunner, Coyote always had ideas. I'm sure sometimes he would think of Euler's formula, especially with some trigonometric calculation, but he always had a plan. So that's Euler's, right? And so that means that in this case, we can think of negative 2t as that angle theta. And so we can write, that's what we do next. We write that part. I'm going to keep this e to the t as a common factor there. But this becomes cosine of 2t. It really is cosine of negative 2t. So maybe let's write one step here. Cosine of negative 2t plus I sine cosine of minus 2t, because of properties of cosine, becomes the same as cosine of 2t. And this is I. Again, because of properties of sine, this negative you can pull out of the sine, and so this is I times sine of 2t. This all multiplies e to the t. So where are we? Well, remember, what we want to do is to use this result. We want to write a solution as e to the lambda t, lambda 1t, e to the lambda 2t. So we just computed e to the lambda 1t. We have to do the same for the other lambda, right? And by doing so, because we have an eigenvalue that has non-zero real parts and non-zero imaginary parts, then this evaluation of exponential evaluated at lambda 1t due to application of Euler's formula brings cosine and sine into the picture. Okay, so we just evaluated e to the lambda 1t. We went through a few steps, and e to the lambda 1t is e to the t times quantity cosine minus I sine. So now we can do the same for the other eigenvalue. So e to the lambda 2t would be e to the 2 plus not 2, e to the 1 plus 2i times t. And due to similar applications of Euler's formula, this becomes e to the t times cosine of 2t plus I sine of 2t. So the only difference is that in the previous evaluation for lambda 1, even the lambda 1 has a imaginary part that is negative, it's minus 2. Lambda 1 has this negative in front of the sign. Lambda 2 has a positive imaginary part, which is positive 2. So we have cosine plus I sine. So what we need to do now is multiply e lambda 1t times v1. So we have e lambda 1t times v1. Let's see what we get here. So this is cosine 2t minus I sine 2t times v1. Let's remember what was v1. So v1 is the vector that has one negative I. One negative I. The good thing about these calculations is that they're tedious. So you have to roll up your sleeves and grab a bunch of paper and pencil. Cosine 2t minus I sine 2t. And then here, minus I cosine positive I square sine. So remember, e to the lambda 1t is a scalar, v1 is a vector, that product is a vector, right? So we could write one additional, so we can write that I square. Let me write this one more line here. The first entry stays the same. This is cosine of 2t minus I sine 2t. And second entry, I squared is negative 1, so this is, we can write here minus sine 2t minus I cosine 2t. Any questions so far? Similar for the other. We need lambda e to the lambda 2, e to the lambda 2t times v2. Right? So this is cosine 2 plus I sine 2t and v sub 2. Let's take a look. What was v sub 2? So v sub 2 is 1i. 1i. So the first entry becomes cosine 2t plus I sine 2t. The second entry has I cosine plus I square sine. So we write, we got one more line. So first entry stays exactly as it was, and this becomes minus sine plus I cosine. So we're almost there. We have to write this as a linear combination of v1 and v2 with coefficients. We need to write this in terms of the coefficients, but that's where we're heading, right? So that means, therefore, hence, we can write x of t. What we want is x of t c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. That's how we want to write the general solution, right? So we're going to write x to be c1 times our previous calculation, then c2 times our previous calculation. So let's see what are our previous calculation. The latter calculation is cosine 2t plus I sine 2t. I'm almost running out of space in here. Minus sine 2t plus I cosine 2t. That was the product, e lambda 2 t times v2. Let's look at the product, e lambda 1 v1. E lambda 1 t times v1 is very similar. Cosine minus I sine. The first entry is cosine minus I sine, and then the second entry is minus sine minus I cosine. This here is minus sine minus I cosine. So we would multiply C1 by the first vector, multiply C2 by the second vector, and then C1 and C2 would be propagated everywhere. But there is one more thing that we had in this exercise that we have not used yet. What would that be? That's what I said at the beginning. Give me a minute, right? I said, give me a minute. Just give me 10 seconds. And I did something there, and I was evil. I put there some initial conditions. Maybe not that evil. So let's use the initial conditions, because the point of using that information would be to find the values of C1 and C2. Yes. Would you press that, please? Yeah.
Where did the e to the t go
in these calculations? Right. You're saying that I left it. Each, yeah, good catch. Let me repeat the question. Question is, what happened to e to the t? Right? In each calculation of e to the lambda 1t and e to the lambda 2t, see, there is an e to the t term which I neglected. That's a good catch. So let me go back here. Lambda 1, so there would be an e to the t over there. So I did neglect that. Thank you for bringing that up. But this is not going to change the calculations too much, because here the calculations that are more tedious are the ones involving the complex parts, the real part and imaginary part, and the cosines and sines. So throughout this, we could hold e to the t as a common factor. You could bring it up, and then all the terms become more messy. But you could also bring it, keep it as a common factor here, e to the t, e to the t. Okay, so it's still multiplying both first and second entry of the vector, but you can keep it as a common factor there. That would happen for e to the lambda 1t v1, and e to the lambda 2t v2 also has an e to the t, right? So which is here, and we can choose to keep it as a common factor like that, which means that in this step here we would have c1 e to the t times this vector c2 e to the t times that vector. So if we evaluate this expression at t equals 0, we will be able to use the initial conditions. Because remember, x of t, when we write x of t, we really mean x1 of t, x2 of t, that's what we mean. By x of t equals something, we mean x1 and x2 at that value of t. So if we evaluate these at 0, so using initial conditions, we would get x1 at 0 and x2 at 0. And the information we had, what is the value of x1? x1 of 0? 2. And x2 of 0? 1? 1 or 0? Oh, no. I'm sorry. It's supposed to be 0. This is supposed to be 0. Let me repeat this again. Sorry, that was a type of mine. So the initial condition is x1 at 0 equals 2, and x2 of 0, x2 at 0 equals 0. I had written another value there, but it's supposed to be 0. Okay? So these two conditions, this value 2 and 0, those are the values we're going to use here. So we're going to say x1 at 0 is 2, and x2 at 0 is 0. Okay, we're going to write that on the left-hand side, and now the right-hand side is evaluating. We're going to evaluate t at 0 on everything that has t here, right? So we have c1 e to the t, e to the 0, that's 1, and then c1 multiplying the vector. That would be cosine of 2 times 0 minus I times sine of 0, so that would be 1, and this is 0. Sine of 0 is 0, cosine of 0 is 1, so this would be minus I. Then we have c sub 2, e to the 0 is 1 times c sub 2, so then cosine of 0 is 1, and minus sine of 0, which is 0, times I times cosine of 0, so this would be I. So using the initial conditions, we evaluate the right-hand side of the expression, which is the general solution, evaluate that at 0, and we get on this right-hand side an expression in terms of those coefficients, C1 and C2, and in the left-hand side, we're writing the values we had from the beginning, the so-called initial conditions. So now we have an equation, 2 equals C1 plus C2, 0 equals C1 times negative I plus C2 times I. So let me write those equations. So we have something that looks like this: C1, 1C1 plus 1C2 equals 2. And here we have something that looks like minus I C1 plus I C2 equals 0. And what we really like to do here is we'd like to solve these equations for C1 and C2. These are now linear equations, not differential linear equations, simply linear equations in C1 and C2, where C1 and C2 are the unknowns, are the variables. They're not, there are two equations, two variables. So one thing that we can do here is form an augmented matrix and row reduce. That's if we were using linear algebra. Well, then let's use linear algebra. So collect here 1 and minus I, 1 I, and then 2, 0. This will take a couple of steps here, not too complicated. I want to create a 0 on entry 2, 1. Okay, I want to create a 0, so I'm going to say, look, I'm going to multiply the first row by I, and then I'm going to add that row to the second row. If I multiply the first row by I get here I, and 2I. So what's being replaced here is the second row. So the first row stays exactly the same with those values 1, 1, and 2. The second row is going to be newer. So when I do this calculation, I times the first row, I have this value I, and added I plus minus I, that gives me a 0. I plus I is 2I, and then 2I plus 0 is 2I. So I successfully created a 0 on that entry 2, 1. And now what I'd like to do is to do something about this entry. I'm going to create a 1 there. That number 2I is not equal to 0. So to create a 1, I'm going to say divide the second row by this number 2I, or multiply the second row by the number 1 over 2I. On all this process, the first row stays the same. Dividing 0 by 2I is 0. 2I over 2I is 1. And 2I over 2I. Hey, did I have this correctly? Yeah. 2i over 2i is also 1. So my next step is to create a 0 on this entry, which is the entry 1, 2. But because I have a 1 on entry 2, 2, it's easy to create a 0 there, okay? And I will create a 0 by saying, look, all I have to do is to multiply the second row by -1, and then add that to the first row and replace the first row. So if I multiply the second row by -1, this is 0, -1, and -1. Okay, so on that operation, the second row stays exactly the same, stays with 0, 1, 1. Okay, and I'm going to add this new row, 0, -1, -1, to the first row. 0 plus 1 is 1, -1 plus 1 is 0, -1 plus 2 is 1. This means, this implies, remember, we started with this system, right, in variables C1 and C2, and we wrote this matrix called augmented matrix. So if I were going to write the equations back, right, so if I read each of these equations, this equation tells me 1C1 plus 0C2 equals 1. And this other equation tells me 0C1 plus 1C2 equals 1. Which means that we have found the value of C1 being equal to 1, and the value of C2 is also equal to that number 1. So therefore, C1 equals C2 equals 1. So for those initial conditions, these are the values of the coefficients that make the solution, make the expression work out, right? So so with those values, then we write using C1 equals C2 equals 1, then we're going to write x of t equals so C1 is 1, and I'm going to have to, and then C2 is also 1. So now I go back and write this ET times cosine, right? So it's cosine minus I sine then minus sine minus I cosine and then for the second vector cosine plus I sine, so this would be cosine 2t plus I sine 2t, and this here will be minus sine 2t plus I cosine 2t. So this is almost what we wanted. Let's now go ahead and multiply that e to the t. So the first vector looks like e to the t cosine 2t minus I e to the t sine 2t. And similar, so here we have minus e to the t sine minus I e to the t cosine. Second vector, we have e to the t cosine plus I e to the t sine. Looks a little messy because I don't have a lot of room here, not as much as I like, but then the second entry is similar. So we would have minus e to the t sine 2t plus I e to the t cosine 2t. Now I bring everything together into one vector, right? So the first vector has two entries. The second vector has also two entries. It's just that my writing here is a little convoluted there, but each of them is a 2x1 vector. So the first entry would be adding the first entries accordingly. So the first entry of this looks like e to the t cosine 2t minus I e to the t sine 2t plus e to the t cosine plus I e to the t sine. That's the first entry. Second entry is minus e to the t sine minus I e to the t cosine minus e to the t sine plus I e to the t cosine. Now, is there anything here that would simplify? Are there terms that can be canceled with each other? Yeah, let's find them, because it will make everything, well, whatever we can clean up, we will. So this minus I e to the t sine can be canceled with this. So one is the negative of the other one. And the other terms, we can add them up. So the other terms are going to be 2 times e to the t cosine of 2t. And then in the second entry, we can also do something similar. Let's see if anything, yeah, there is this term, I e to the t cosine is negative there, and here we have I e to the t cosine positive, so they are going to cancel. And the other terms are also going to add up. They don't cancel, they add up, so this becomes minus 2 e to the t sine of 2t. And so this, what we're finding is that this is equal to x1 of t and x2 of t. In other words, x1 of t is 2 et cos 2t, and x2 of t is minus 2 e to t sine 2t. Where these functions x1 of t and x2 of t these are the functions that satisfy this system of differential equations with these initial conditions.